In this video, we're going to talk about diagonalization and the actual process that's going to be used to diagonalize a matrix if it's possible. I want to remind you of the theorem that we talked about in the last video about when a matrix is diagonalizable. If you have an n by n matrix A, and suppose that A has eigenvalues lambda 1 to lambda k, where k is less than or equal to n, then it turns out that the matrix is diagonalizable if and only if the sum of the dimensions of the eigenspaces is n. Remember that diagonalizable means that A is diagonalizable, means that A is similar to a diagonal matrix, and similar means that you can write A as a product of these three matrices, P times D times P inverse. It's important that P and P inverse are inverses, of course, and then D is a diagonal matrix. So remember that D being diagonal just means that all the values off the main diagonal are 0. So you have zeros over here, all the way down, and likewise over here. Okay, so zeros all the way except for possibly the main diagonal. It's possible that the values on the diagonal are 0 as well, but the important thing is that all the values off the diagonal have to be 0. So that's a diagonal matrix. So if A is similar to a diagonal matrix, it's diagonalizable, and it turns out that we have a nice, neat theorem that tells us when a matrix is diagonalizable. We also have a nice corollary to that theorem that says that if we have n distinct eigenvalues, where n is again the size of the matrix, A is an n by n matrix, if A has all distinct eigenvalues, then A is diagonalizable. Okay, and that's because the dimension, the reason why this works is that the dimension of the eigenvalues has to be 1. Because if you have n distinct eigenvalues, that means that each of the eigenvalues is a unique root to the characteristic polynomial or the characteristic equation. And the dimension of the eigenspace has to be at most, it has to be always greater than or equal to 1, but at most the multiplicity of the eigenvalue. So if you have distinct roots, that forces the dimensions of the eigenspaces to all be 1, and therefore they have to add up to n. So that's a quick sketch of that corollary right there. What I want to do in this video, though, is I want to go over all the examples that we've talked about. So this might be a little bit longer video, but what I want to do is I want to go over, we've gone over some computing eigenvalues and eigenspaces for different matrices, and I want to just leverage that and talk about the diagonalization process. So we're going to start by looking at the 2x2 matrices. So we're going to do 6 examples here. The first example, we're going to talk about the first 2x2 matrix that we studied. And so what we want to do is we want to diagonalize the matrix A, where A is 2, 5, 1, negative 2. And when I say diagonalize, I'll always word this better on the exam, but if possible, diagonalize. It's not always possible. We have a criteria that tells us when it is and when it isn't possible. But if possible, diagonalize A. So that means that what we're looking for is the matrices P and D, and once we have P, then we can quickly compute P inverse. So what we're going to do is remember that we had our eigenvalues for this matrix A. Our eigenvalues happen to be 3 and negative 3, and 3, the eigenspace corresponding to eigenvalue 3 was the span of the vector 5, 1, and the eigenspace corresponding to the eigenvalue negative 3 was the eigenvector, so this was spanned by the eigenvector 1, negative 1. And it turns out that what we're going to do is we're going to use these vectors that span the eigenspace to form P. So P is going to be the matrix 5, 1, and 1, negative 1. So what we're doing is we're taking our columns, 5, 1, and putting that in the first column of P. And the second column of P is going to be the other eigenvector, 1, negative 1. Okay, and so that's going to be P. So the columns of P are exactly the eigenvectors that we get corresponding to the different eigenvalues. And it turns out that the diagonal matrix D is going to consist of the eigenvalues that we get. And since we use the first column in P for the eigenspace corresponding to lambda equals 3, that means that this value will be 3. And since the second column of P was the eigenvector corresponding to lambda equals -3, that means that -3 goes there. So our diagonal matrix that A is similar to is 3, 0, 0, -3, and again, those are the eigenvalues. And it turns out that if we compute the inverse, and you can do this many ways. We know how to easily compute inverses of 2 by 2 matrices. So I'll leave that to you to figure out exactly how to do the inverse, but the inverse happens to be 1/6, 1/6, 1/6, and -5/6. I also want to point out something really neat that happens. Notice that P, in order for A to be diagonalizable, we have to find an invertible matrix P where this is possible. And it turns out that P is going to be invertible in this case because what happens is that the eigenspaces are spanned by linearly independent vectors. And we know that if we have linearly independent vectors, that so if our vectors are linearly independent, the determinant that we get of that matrix, where we take the matrix of which is the columns, right? So the determinant that we get by this matrix has to be non-zero, and therefore has to have an inverse, and everything works out perfectly well. And it turns out, if we check this, and I'll leave this again to you to check. When I say I'll leave this to you to check, what I mean is pause the video, write it down on a sheet of paper, and multiply out these 3 matrices. But it turns out if you multiply these, so if you take 5, 1, 1, -1, times 3, 0, 0, -3, times 1/6, 1/6, 1/6, -5/6, and you multiply all of those, what you're going to get is 2, 5, 1, -2, just like we wanted. Okay, and so that's how we diagonalize a matrix. So D is going to be the diagonal matrix consisting of, so the diagonal entries are going to be the different eigenvalues, and P is going to be the matrix whose columns are the corresponding eigenvectors. And that's how the diagonalization process works. All right, so that's example, I'll call this example 1. Example 2 is actually going to be for a matrix that we have not, we did talk about the eigenvalues. So this is going to be for the matrix, 2804. We did talk about the eigenvalues. We did not talk about eigenspaces, but let's just do that very quickly. So if A is the matrix 2804, our eigenvalues are going to be the diagonal entries 2 and 4. It turns out, and you should check this, I really do want you to pause the video, write this down on a sheet of paper, try and find the eigenspaces. It turns out that the eigenspace corresponding to lambda equals 2 is going to be the span of the vector 1, 0. And the eigenspace corresponding to lambda equals 4 is going to be spanned by the vector 4, 1. Okay, so do check those. Make sure that I'm not lying to you. I'm not lying to you, of course, but you should check those. So it turns out that our matrix P that we're going to be looking for is going to be the matrix whose columns are 1, 0, and 4, 1. D is going to be the diagonal matrix corresponding to the eigenvalues 2 and 4, so 2, 4. And if this is P, then P inverse happens to be 1, -4, 0, 1. I want to point out that the diagonalization process is not unique. I could have easily switched the role of 2 and 4, in which case I also could have had, I haven't computed the inverse here, but I could have also had P be 4, 1, 1, 0, in which case D would have had to also been switched. It would have been 4, 0, 0, 2. Right, the eigenvalue 4 is the one that led us to the eigenvector 4, 1. And then P inverse would be whatever it is. P inverse would be, in this case, it's easy enough to compute. You switch the entries on the main diagonal, so it's 0 and 4. And then you're going to multiply the non-zero entries by or the non-diagonal entries by -1, and then finally I have to multiply everything by the determinant of the original matrix P, which is -1. So that makes it 0, 1, 1, -4. So it turns out that's our inverse. And you can check that again, P times D times P inverse will give us A in either choice that we have. And there's more choices that we have than this. So if you remember, I could write E2 as actually the span of any multiple of that vector, as long as it's not at the zero vector. The span of the zero vector is just the zero vector. But any other non-zero multiple of that vector will have the same span. Likewise with this eigenvector 4, 1. I could put 8, 2, or 1, 1/4, whatever, or -4, -1, whatever that eigenvector is that I want it to be, any non-zero multiple of this eigenvector will work. That does change the matrix P, which will change the matrix P inverse, but the overall process is the same. Okay, so that is example 2. And then our last 2x2 example that I want to talk about, which I'll call example 3, is one where this is one that we have not actually computed anything with. But I thought that this was worthwhile just to talk about. Let's say that I have a matrix A, which is 2, 5, 0, 2. So A happens to be an upper triangular matrix. The only eigenvalue that we're going to get is 2. And if we look at the eigenspace E sub 2, this is going to be spanned by the vector 1, 0. So this is going to be an eigenspace of dimension 1. This is the only eigenvector, so the sum of the eigenspaces is just 1, which is less than 2. And therefore, A is not diagonalizable. A is not diagonalizable. Okay, so there is no diagonal matrix similar to A. That's all there is. So that's all there is to say. All right. Example 4, what we're going to do now is we're going to switch to 3x3 matrices. And again, we've already done all the work here. Let's just leverage what we know. So I'm going to start with a matrix that's 0, 0, -2, 1, 2, 1, and 1, 0, 3. This is the matrix that we started with when we originally were doing 3x3. And we know that our eigenvectors were 1 and 2. 2 was an eigenvector of multiplicity 2. And remember that E2, the eigenspace E2, was spanned by the vectors -1, 0, 1 and 0, 1, 0. So that means that A is diagonalizable, because if you were to take, this is a 2-dimensional eigenspace, lambda equals 1 corresponds to a 1-dimensional eigenspace, because I always have to have dimension at least 1. And therefore A is diagonalizable, because if you add up the dimensions of the eigenspaces, you get 2 plus 1, which is 3. A is a 3x3 matrix, and we are good to go. So E2 is the span of those two vectors. I should also add the E1 we determined was the span of the vector -2, 1, 1, or really any non-zero multiple of that vector would work. And therefore, the matrix P that we're going to use to diagonalize the matrix P is going to be -2, 1, 1, -1, 0, 1, 0, 1, 0. You can actually interchange these columns in any order that you'd like. You just have to put your matrix D in the right order. So since the first column, -2, 1, 1, corresponds to the eigenvalue 1, the value 1 goes in the first column of D. And since the other two vectors correspond to the eigenvalue 2, 2 goes in those columns. And the rest are zeros because it's a diagonal matrix. It turns out that for this particular choice of P, P inverse is going to be the matrix -1, 0, -1, 1, 0, 2, and 1, 1, 1. Okay, multiply these together. You really should check that if you take P times D times P inverse. These are just really simple matrix multiplications, but they're worth checking. It's very satisfying to check that this all works. You really do get A. And that is how that works. Two more examples. So our next example, which I'll call example 5, naturally. Our next example is the matrix A, which is 4, 3, 1, 5, 2, 5, 0, 0, 2. And remember that this was a matrix which had eigenvalues -1, 2, and 7. We have 3 distinct eigenvalues for a 3 by 3 matrix, therefore it's diagonalizable. There's no question, we don't have to check anything we know already, based on the corollary to the theorem that it's diagonalizable. And it turns out that E sub -1, so the eigenspace corresponding to -1 was spanned by 3, 5, 0. 3, -5, 0. E2 was spanned by 3, -1, -3. And E7 was spanned by the vector 1, 1, 0. So the E7 was the span of the vector 1, 1, 0. And that means that we can make P. I'm not sure why I picked this order for the eigenvalues, but this is the order that I picked, so therefore this is the inverse that I've computed. But if we take 3, -1, -3 as the first column, the second column is 1, 1, 0, and the third column is 3, -5, 0, then we're forced to pick our diagonal matrix to be 2, 7, -1, and the rest zeros. And then this would force P inverse to be 0, 0, -1/3. The determinant of A is, 8 minus 12, -4, -8. So you're going to have eighths in this. So you get, 2 times -4, -8 is your determinant. So anyways, we have some fractions here. So we get -1/3, 5/8, 3/8, 1/2, 1/8, -1/8, and 1/6. Okay, so that's P inverse. And again, check. You really should check that if you take P times D times P inverse, you get A. And everything works out. It's very satisfying to check that you get that. Our last example is, so let's call this example 6, was where A was the matrix 3, 2, -1, 0, 4, 1, 0, 0, 4. And so if we look at our eigenvalues are going to be 3 and 4, and 4 is of multiplicity 2. So what we have to do is we have to look at the eigenspace. This is not one that we've computed before, so I think this is worth just going over, but let's try and find E4. And what we're going to do is we're going to look at solving A minus 4I times x equals the 0 vector, and we'll do this in augmented matrix form. So if we take A minus 4I, what we're going to do is we're going to subtract 4 from all the values on the main diagonal. So that'll give us -1, 0, 0. The rest of the values will be the same, so the off-diagonal values don't change. So -1, 2, -1, 1, 0, 0, 0. And it turns out that when we simplify this, what we're going to end up with is 1, -2, 0, 0, 0, 1, 0, 0, 0. And so if you think about what are the solution sets here, well, you have to have x3 is 0. Let's call x2 t, and x1 is then going to be 2t. Maybe we did actually go through this process of finding the eigenspace, maybe not. But you have one parameter here. That means that your eigenspace is going to be one-dimensional. So E4 is going to be the span of the vector 2, 1, 0, which is one-dimensional. So since the dimension of E4 is 1, but lambda equals 4 had multiplicity 2 in the characteristic equation P of lambda equals 0. Since lambda equals for odd multiplicity 2, A is not diagonalizable. And there's not much more to say. So A is not diagonalizable. Okay, so those are the examples of diagonalization that I wanted to cover.